In this longer version, I want to build 2 layers. First, the clean heap solution that is excellent for interviews. Then the harder quickselect follow-up that brings average time down to linear. The problem gives us up to 10,000 points and asks for the k closest to the origin. The result order does not matter, which is a big hint that we do not need a fully ordered final array. The first observation is free performance. We never need true Euclidean distance. Comparing x squared plus y squared gives the exact same ordering, because square root does not change which value is larger. I like to organize this problem into 3 levels. Sorting is the easiest baseline. The heap approach is the most interview-friendly optimization, and quickselect is the harder follow-up when they push for average linear time. Here is the simplest picture. 1, 3 has squared distance 10, minus 2, 2 has squared distance 8, so minus 2, 2 is closer, and we reach that answer without any square root. Sorting is my baseline answer. It is correct, compact, and sometimes enough, but it fully orders the entire array, which means it does more work than the problem really asks for. Now for the main solution I would actually present. Use a heap of size k. Every point gets considered, but the heap never holds more than k candidates. The moment it grows too large, we eject the farthest one. As the mental model, the heap contains the survivors. The root is the worst survivor, meaning the farthest point among the current top k. If something better arrives, that worst survivor is the one we want to remove first. Let us trace the second example. 3, 3 gives 18. 5 minus 1 gives 26. Minus 2, 4 gives 20. Since k is 2, once all 3 have been seen, the point with 26 gets kicked out. This is a subtle but important interview point. We are not trying to repeatedly extract the closest point. We are trying to protect the closest k points, so the heap top should expose the current farthest survivor. The first half of the heap code is extremely short. Compute the squared distance and push negative distance together with the point. Then apply the heap size rule. If the heap ever grows past k, pop once. At the end, return the points remaining in the heap. Here is the complete heap answer in one screen. In most interviews, this is already a very strong solution, because it is efficient, simple, and easy to explain clearly. Now for the harder follow-up. If the interviewer asks for average linear time, quickselect is the next step. The goal is no longer to maintain a running top k. Instead, it is to partition until the first k positions contain the answer. This is the quickselect picture. After partitioning, every point on the left is no farther than the pivot, and every point on the right is farther. If the pivot ends up at k-1, the first k points are exactly what we need. The reason quickselect fits this problem is that the answer may be returned in any order. We do not need the first k points sorted. We only need them to be the correct set. Partitioning gives us exactly that. The optimized code starts with a small distance helper and a partition function. The partition uses the rightmost point as the pivot distance. Inside partition, every point whose distance is less than or equal to the pivot goes to the left side. Then the pivot is swapped into its final position and we return that pivot index. Then quickselect keeps shrinking the search window. If the pivot is too far left, move right. If it is too far right, move left. Once the pivot lands at k-1, the first k points are the answer. And here's the full quickselect solution in one screen. This is the optimized follow-up answer when you want average O of n time, and you are comfortable explaining partitioning. The best interview strategy is to have 2 levels ready. Lead with squared distance and the heap of size k. Then, if they push further, explain quickselect and why unordered output makes partitioning enough.